The journey to Mars has long captured the human imagination, a red dot in our night sky that beckons us to explore. Yet, for all our ambition, we remain bound by the immense gulf of space separating our worlds. With current chemical rocket technology, a one-way trip to Mars takes between 6 and 9 months. This isn't just a test of patience, it's a fundamental barrier to human exploration. Such a long voyage exposes astronauts to a relentless barrage of cosmic radiation far beyond the protective shield of Earth's magnetic field, significantly increasing their lifetime risk of cancer. It is a silent, invisible threat that accumulates with every passing day, making speed not a luxury, but a necessity for survival. Beyond the radiation, the crew must endure prolonged exposure to microgravity. This weightless environment takes a heavy toll on the human body, causing muscles to atrophy and bones to lose density. Upon arrival, astronauts would be physically weakened, compromising their ability to perform critical tasks on the Martian surface. Furthermore, the long transit time severely restricts our operational flexibility. Earth and Mars align for optimal travel only once every 26 months, creating narrow launch windows. If a mission misses its window, it faces a 2-year delay. Imagine instead a journey that takes just 3 months. This isn't science fiction. It's the tangible promise of new technologies being developed and tested today. Having the travel time would slash the crew's exposure to deep space radiation, mitigating one of the most significant health risks. A shorter trip also means less time spent in the debilitating environment of microgravity, ensuring astronauts arrive on Mars stronger, healthier, and better prepared for the challenges of exploration. It changes the equation entirely, shifting Mars from a distant, perilous outpost to a reachable destination. The dream of a 3-month trip to Mars is closer than ever before, thanks to a convergence of revolutionary advances in spaceflight. The period between 2024 and 2025 in particular has been marked by a series of quiet but momentous achievements. These are not theoretical concepts anymore. They are real-world hardware demonstrations and critical system tests. From nuclear reactors roaring to life in simulated space conditions, to spacecraft successfully transferring fuel in orbit, the building blocks for rapid interplanetary travel are being assembled right now. These breakthroughs signal a pivotal shift, moving the goal of a crewed Mars mission from a distant aspiration into a concrete engineering project with a plausible timeline. To conquer the vast distances of our solar system, we need a complete overhaul of our approach to deep space travel. This transformation is being driven by 3 interconnected areas of technological advancement. The first, and perhaps most powerful, is the dawn of nuclear propulsion. Unlike the controlled chemical explosions that have powered rockets for a century, nuclear thermal propulsion and nuclear electric propulsion promise to be 2 to 3 times more efficient, providing the high thrust and sustained power needed to drastically shorten the interplanetary journey and make a 3-month Mars trip a reality. The second critical breakthrough is in-space refueling. The solution is to launch a spacecraft with only enough propellant to reach orbit and then fill its tanks at an orbiting gas station. This capability, recently demonstrated for the first time on a large scale, unlocks the ability to send massive payloads to Mars. Larger habitats, more scientific equipment, and enough fuel for the return journey. Without refueling, a sustainable human presence on Mars remains a logistical impossibility. Finally, the third pillar is the rise of hybrid and fully reusable launch systems. Companies are pioneering rockets that can fly to space, return to Earth, and be prepared for another flight in a short amount of time. This reusability drastically lowers the cost of accessing space, making it economically feasible to launch the multiple missions required for a Mars campaign: fuel tankers, cargo shipments, and crewed vehicles. This essay will explore how these three breakthroughs are not just independent advancements, but a synergistic trio. We will delve into the recent tests and demonstrations from 2024 and 2025 that have proven these concepts are viable. By examining how these technologies integrate, we will paint a clear picture of how humanity can cut the Mars travel time in half, making crewed missions not only faster, but also safer and more sustainable than ever before. To dramatically shorten our journey through space, we need an engine that breaks from the past. This is where nuclear propulsion enters the picture, offering a revolutionary leap in performance. There are two main concepts being developed: nuclear thermal propulsion, NTP, and nuclear electric propulsion, NEP. Both use the sustained, intense energy from nuclear fission, but they apply it in very different ways. Nuclear thermal propulsion, or NTP, is the sprinter of the two. A compact nuclear reactor acts as a superheater. It heats a lightweight propellant, typically liquid hydrogen, to extremely high temperatures. This superheated hydrogen gas is then expelled through a nozzle at tremendous speeds. The key advantage of NTP is its high specific impulse. It can produce twice the efficiency of the best chemical rockets. On the other hand, nuclear electric propulsion, or NEP, is the marathon runner. In an NEP system, a nuclear reactor doesn't heat the propellant directly. Instead, it generates a large amount of electricity. This electricity powers highly efficient electric thrusters, such as ion drives or plasma drives. While the thrust at any moment is very low, often compared to a piece of paper on your hand, it's continuous. Over months, this gentle but relentless push can accelerate a spacecraft to much higher speeds. An engine is only as good as the materials it is made from. In 2025, a series of critical experiments demonstrated nuclear fuels capable of handling the infernal environment inside an NTP reactor. A landmark achievement came from General Atomics. They took specially designed nuclear fuel samples and subjected them to conditions mimicking the heart of an NTP engine. Hot hydrogen gas was blasted through the samples in 6 thermal cycles. Temperature was rapidly ramped up to 2,600 Kelvin. The fuel was then held at this peak for 20 minutes. The results were exceptional. The fuel survived the punishing cycles and performed flawlessly. The tests confirmed the materials maintained structural integrity and did not degrade under intense heat and corrosive hydrogen flow. Further analysis showed the fuel could likely perform at nearly 3,000 Kelvin. This is critical because NTP efficiency is directly tied to operating temperature. Achieving such temperatures would enable engines 2 to 3 times more efficient than chemical rockets. These tests by General Atomics represent more than a successful experiment. They are a proof of concept that the material science behind NTP is sound. With these hot fire tests, we've moved from design to validated hardware. Building a nuclear rocket requires more than just high-performance fuel. Specialized facilities are being built to simulate a nuclear rocket environment. One such facility is a high-temperature test bed at Oak Ridge National Laboratory. It lets researchers test materials like zirconium carbide in vacuum, exposing them to intense heat and radiation. The test bed reaches about 4,000 degrees Fahrenheit. That closely replicates an NTP reactor's operating environment. NASA has fostered a competitive industrial base. In 2021, the agency selected 3 companies: BWX Technologies, General Atomics, and Ultra-Safe Nuclear Technologies, and again in 2025, narrowing to the most promising teams: General Atomics and Standard Nuclear. The roadmap for the next decade is clear. Through the late 2020s, the focus is completing ground-based testing, then a push for a dedicated flight demonstration mission to prove NTP is a mature technology, ready to revolutionize exploration. Even with the incredible power of nuclear propulsion, a mission to Mars is still bound by a fundamental law of physics known as the tyranny of the rocket equation. The solution is elegantly simple. Don't launch everything at once. In-space refueling is the technology that breaks this tyranny, acting as a gas station in orbit. A large interplanetary ship can be launched into low Earth orbit with its fuel tanks nearly empty. Then, in a series of subsequent launches, smaller dedicated tanker vehicles can fly up to meet the ship and top off its tanks. In-space refueling is the key to a round-trip ticket. A separate, pre-deployed tanker could be waiting in Mars orbit to refuel it for the voyage back to Earth. That all changed in March of 2025, when SpaceX conducted a pivotal orbital propellant transfer demonstration with its Starship vehicle. This test marked a historic moment, proving that the concept of an orbital gas station was not just theory, but a practical reality. Once securely docked, the critical phase of the test began. The transfer of cryogenic liquid methane and liquid oxygen from the tanks of the tanker Starship to the receiver Starship. The operation was a resounding success. SpaceX demonstrated its ability to control the flow of super-cold liquids in a zero-gravity environment, managing pressures and temperatures to ensure a stable and efficient transfer. It provides mission architects at NASA with a proven, tangible capability they can now incorporate into their plans. This single event dramatically de-risked the logistics for future deep space campaigns. The combination of high-efficiency nuclear propulsion and proven in-space refueling allows us to completely redraw the map for a human mission to Mars. The fully fueled nuclear ship fires its engine. It propels the crew on a fast 3 to 4 month transit to Mars. That fast transit minimizes radiation and microgravity exposure. Upon arrival, the crew descends to a pre-established site where this reactor already provides constant, reliable power. That power runs their habitat and begins in situ resource utilization. Reusable launchers lower the cost. Orbital refueling becomes viable. Refueling enables nuclear rockets. Nuclear rockets improve crew safety. Payload capacity delivers surface power. Surface power enables ISRU. The system becomes sustainable. The road to developing new and reliable space hardware is rarely a straight line. This approach was starkly illustrated by the maiden flight of Gilmour Space's Eris rocket in July 2025. While the launch was not a success, it was far from a total loss. In the world of aerospace engineering, data is gold. The 14 seconds of flight provided Gilmour's engineers with a wealth of information. Leading the charge in reusability is Relativity Space, which has made significant strides with its Terran R rocket. In early 2025, Relativity reported major progress, hitting key milestones in the development of its reusable Aeon R engine. Another critical need is testing the long-duration systems required for deep space. This is where recoverable orbital platforms play a vital role, like the European Space Agency's Space Rider. At the end of its mission, it is designed to autonomously re-enter the atmosphere and perform a gentle, precise landing on a runway, allowing scientists to retrieve their experiments and engineers to inspect the vehicle itself. We stand at the threshold of a new era in space exploration, one where the vast distances of our solar system are beginning to shrink. This transformation is not the result of a single, magical invention, but rather the powerful synergy of three distinct, yet deeply interconnected, technological revolutions. The synthesis of these three pillars, propulsive power, orbital logistics, and affordable launch, creates a comprehensive architecture that addresses the fundamental challenges of sending humans to Mars. This staged, incremental approach provides a logical window for the first crewed mission to Mars to leverage these combined technologies in the early 2030s. The technologies to cut the Mars journey in half and build a sustainable presence on another world are no longer distant fantasies. They are being built. They are being tested. They are being proven in labs and on launch pads today. The final ingredients required are a shared vision, a commitment to collaboration, and the collective will to take the next bold step and begin humanity's next great chapter in the cosmos.